So it's a great pleasure to welcome Dave Penneys for the opening ceremony of the 2017 program on operator algebras subfactors application.
Thank you so much for inviting me to speak here, for organizing this wonderful semester here. This is fantastic. It's a great honor to give these talks, and I hope you find it useful and correct. Anyway, so yes, please stop me and ask questions at any time that you you like. Today, I'm trying to keep it very basic. Since Yasu will be talking about type 3 and Tomita Takasaki and everything, and I'm doing kind of the Vaughan Jones subfactor theory type stuff, I'm going to stick mostly in the world of finite von Neumann algebras. Okay, so these have traces, and I'm going to use this it's kind of, it's not necessary for the stuff I'll talk about today, but it makes it a lot easier, and so I'm going to do that. I'm going to make life easy for myself. So first, let's talk about von Neumann algebras. What's a von Neumann algebra? So the Neumann algebra, okay, it's a unital star code subalgebra. A contained in B of H, such that A is A double prime, right? So A prime is the commutant of all of the operators in B of H, such that they commute with A. Okay, so here's some, that's got to move back just a little bit. Now we also can see better. Okay, so here's some exercises, because any good course has to have exercises along with it. Exercises, so...
This is probably going to be the only one I can do, I suspect.
I think you've already done this one. So if S is a subset of T, then T prime is contained in S prime. Okay, that's an easy one. 2, S prime is equal to S triple prime. Okay, so these are important exercises to do for commutants, and play around with it. It's not so difficult. Okay, great. So that's a von Neumann algebra. We can talk about some examples, but we may as well talk about some examples. Why not? So, e.g., so I can take some measure space x mu, and I can take an infinity of x mu acting on L2 of x mu. Okay, so that's one example. 2, I can take a gamma countable group. Okay, here I can take L2 gamma, which is the set of functions with complex numbers which are summable, square summable. Okay, and now I can act via elements, so I can take lambda h, I'll take lambda g, I can act on C, I evaluate it at the point h, or at the element h. This is defined to be C of g inverse h, it's the group multiplication law, and it's easy to see that this is a unitary operator. And now I can just take L gamma, which is just the set of lambda g prime. When I take a commutant, if I take a commutant, it actually turns it into an algebra, because it's easy to see that if something commutes with it, then take two things that commute, their sum is also going to commute. Any multiple commutes, so it's easy to see to be an algebra. If this set is star closed, it's easily seen to be a star algebra, and it's also a Neumann algebra by our definition here, together with an exercise here. I should also say there's the bicommutant theorem. Which says for a unital star closed subalgebra A contained with B of H. The following are equivalent. 1, A is a double prime. 2, A is closed in something in, let's just use the strong operator topology. That's the only one I'll write. There's lots of equivalent other things, but we here we say that A lambda, so it takes a net, it goes to A in the strong operator topology if and only if A lambda C goes to A C for all C in H. It's the topology of pointwise convergence. Okay? So, great. So that's basic von Neumann algebra stuff with some basic examples here. Now so as I said, I was going to focus on finite von Neumann algebras. Von Neumann algebra A is called finite if it has a faithful, well actually, so I want to say a pair of, so it's a pair of things. So we'll say a finite von Neumann algebra is a pair. A trace A with A of the Neumann algebra and trace A the faithful normal tracial state. Okay, now having this tracial state around, this faithful normal tracial state around, makes everything I'm going to do today a lot easier. Again, not necessary for the things I'm going to do today, but we should probably explain what all those words mean for people who are not familiar with that. So let's say faithful. So faithful is trace of A star A is always greater than or equal to 0. This is also state, and it's equal to 0 if and only if A is 0. So this is faithful together with positive. By the way, this trace A is going from A to the complex numbers. Okay. So, normal means if A lambda increases to A, trace of A lambda increases to A. So this is taking some positive net of operators. Sorry?
Place of it.
Trace of A. Thank you. Good. And so this is normality and tracial. Trace of AB is trace of BA. And finally, we have the state properties. Well, just saying it's normalized. Trace of 1 is 1, but sometimes I'll work with non-normalized traces. Here, capital trace is not necessarily normalized. Okay, so at some point I might need to use a capital trace, and it might actually be a weight rather than a state. Okay, so that's the difference between lowercase trace and uppercase trace.
Is A lambda, this normal?
What?
But when you say A lambda increasing
A lambda is positive.
increasing and converging in strong operator topology?
If you have yes. So if it's increasing, if you have a net of positive operators increasing, then it's going strongly if and only if it goes weakly, if and only if there's, There's a notion of increasing, which is, so I can say strongly going, but it's also, the notion of increasing, that's actually a really good question. We say A lambda increases to A, if and only if, so usually you say this is for every vector in H, you take the vector state corresponding to C, and that this increases to, so first of all, these are all positive, right? So this is always greater than or equal to 0, and this increases to, okay, so it's not exactly, my notation is a little bit different, but you can show that they go strongly. Great, so that's finite von Neumann algebras. Also, this is an introduction to subfactors. So I should tell you what a factor is. A factor is a von Neumann algebra with trivial center. So instead of A, it's just the complex unit, the complex scalars times 1. Now, it's important to note that von Neumann algebras come in pairs. All right, so you have A and you have A prime. Okay, so A prime is also the Neumann algebra, right? By property 2 above and the fact that if A is star closed, then A prime is also a star subalgebra that's also weakly closed. Well, anyway, it's a von Neumann algebra, and the point is that they have a common center. Okay, so that's easy to see that center is just A prime intersect A. Just write out the definitions algebraically, and you'll see that that's the center of this algebra. Okay, so this also says that factors come in pairs. And every time I have a factor A, its commutant is also a factor. Okay, because they have the same common center again. So let's give an example of some factors. The first one is just B of H for any Hilbert space. So for example, if H is if it's n-dimensional, less than infinity, then B of H is just, the n by n matrices over C, and that's what's called a type 1 n factor. These are called the type 1 factors. Well, anyway, type 1, there's type 1 n depending on if you're n of C, you're type 1 infinity if you're B of H for H, infinite dimensional, and we're going to assume all our Hilbert spaces today are separable, just to not deal with anything too large, okay? Great. Here's a second one. I take gamma, a countably infinite ICC group. I didn't actually give you examples of finite von Neumann algebras, so let's actually do that too. So let's say instead of this, so gamma is a countable group. We saw how to get L gamma, right? And this is actually finite. What's the trace on L gamma? It's the indicator, I use the vector state, which is the indicator function at the identity. So delta E at G is just the product of delta symbol, delta G is E, okay? So this actually defines this, it's easily seen to be faithful, normal, tracial, and a state, okay? So if now L gamma is a factor, if and only if gamma is ICC. ICC stands for infinite conjugacy class, okay? So that means all non-trivial conjugacy classes are infinite with the exception, all non-trivial ones, right? So the conjugacy class of the identity is trivial, all the other conjugacy classes are infinite, and this is a nice exercise to do that. And if you want to hint, most von Neumann algebra books would have it. Any Vaughan Jones notes on von Neumann algebras has this done very nicely. Okay, so that's great. Any questions? How are we doing? All okay so far? All right, so now we're going to go into the standard representation of a finite von Neumann algebra. So and this is really where having the trace comes in really, really handy. Because otherwise I'd have to do some kind of Tomita-Takasaki theory, and then also will do that. So having the trace just makes it super easier. So I start with A with this faithful normal tracial state, okay? And then I'm going to form the GNS Hilbert space. Vaughan Neumark-Stiegel, that's what that stands for. What I do is I take A together with the following inner product. Okay, so I define this this is a positive definite sesquilinear form on A. It gives me a norm, which is defined to be, take the inner product of A with A, that's the norm 2 squared, and then I complete. And it gives me this thing called L2A. All right, this is the A closed in norm 2. All right, so this is a Hilbert space. Now, we're going to write omega for the image of 1 in L2A. Okay, so it helps to have this other notation around because you want to think of a vector, sometimes you want to think of it as vector, sometimes you want to think about it as an operator. So let's just write that down so that no confusion arises. So now A acts on L2A. Find the left regular representation. So for every A, I just define A acting on B omega is just A B omega. Okay, so we have to see that this is bounded. Well, it's just the trace of B star, A star, A, B. And now I use the positivity of trace. This is less than or equal to the norm in the von Neumann algebra of A star A times the trace of B star B. So this is norm A squared by the C star axiom times the 2 norm of B squared. And that tells me that the left action of A is bounded. Okay. Moreover, this is it's easy to see that this is a normal representation. So in other words, you actually get an action of the von Neumann algebra A on L2A. Okay, so this is actually a normal representation.
Can you remind me what does normal mean there?
Ultra-weakly continuous. So it means that, you know. Okay. So, any other questions? Also, it could mean you have this increasing property, right? If A lambda increases to A lambda is net of positive operators, then when I look over, then the images increase as well. Or completely additive, there's a lot of different equivalent notions of normality. What's interesting about the fact that I'm using a trace here is that I can see that the right action is also bounded. And this here really is going to use the tracial property. So, so I guess I call this lambda, I should call this lambda A. If I take rho A acting on of B omega, this is going to be B A omega. And now I should check that that's bounded. But now it's in the opposite order. And there's no type of inequality here when you have this kind of order. In general, if you're not using a trace, this is going to fail to be bounded, and you're going to have to use the Tomita operator in order to get a right action. Here, this is equal to, because we have a trace, I get to switch it around, and then again, if we see that it's less than or equal to. Okay, so it turns out that we get this action on the left and on the right by A. Okay, and now we go for, I guess, right, so here we have what's called the modular conjugation. In our story, it's very easy. There's a map J going from L2A to L2A by A omega maps to A star omega. And this is easily seen to be an isometric and antilinear, and it's obviously onto a dense subspace. So I call this as an antilinear unitary, really. It's really invertible. Okay, so it's an antilinear unitary. And what we see is if I take J lambda A J acting on B omega, well, one easily calculates it's J lambda A B omega B star omega. That's J of A B star omega. Here I want lambda A star. Let's put a lambda A star there. A star. Now I take J of that, I get B A omega. So what this tells me is that J lambda A star J is row A. Okay, so fantastic. And now, since left and right multiplication commute, this implies that JAJ is certainly contained in A prime. Unfortunately, I've written too low on the board, so now I have to, again. Okay. Now's a good time to ask any questions. I have to erase a board. All right. Okay. So the theorem, first interesting theorem, so maybe here I should put lambda of A. So JHA is, this is row of A, and A prime, this is lambda of A prime, right? So row of A is contained in lambda of A prime. The theorem is lambda of A prime is row of A. So what this is saying is, we've got L2A, I have A acting on the left by lambda, I have A acting on the right by rho. We're going to suppress lambda and rho after this theorem. And for the remainder of time, we're just going to identify A with its image acting on L2A whenever we want to. But that actually, this action of A and that action of A are each other's commutons. Okay? So I'm just going to tell you the steps of the proof. And it's a wonderful exercise to do because it's really just, it's really easy. To do this, it's really just a formal exercise. So I encourage you to go do it if you've never done this before. So step one is to show that JAJ, so you're going to show JAJ prime. This is my row of A prime. So you have to show the other containment, right? You have to show, we know one direction, right? We know row of A is contained in lambda of A prime, so you want to show that lambda of A prime is contained in row of A. You do that by showing row of A prime is contained in lambda of A. Okay, so you show JAJ prime, which is row of A prime, is equal to J of A prime J. Okay, so that's the first step. You show this. And you just do this by taking, taking inner products against the dense subspace capital A omega. All right, so you can just do that. The second thing you do is you say for every x in, so A prime, I write, that's always lambda of A. So I should be telling you which one I mean. That's lambda of A. This is lambda of A prime. For all x in lambda of A prime, Jx omega is x star omega. Again, just take inner products, that's an easy thing to do. 3, for every x in lambda of A or lambda of A prime, Jxj star is Jx star j. All right, and then 4 is when you verify that J lambda of A prime, J, is contained in lambda of A. Okay, and that this is row of A prime, so that's the other direction. Okay, so you do these in this order, and they're all just, you can just do them by taking inner products against the dense subspace capital A omega. Okay, so just if you just do this, you can prove all of these 4 things. You know that 2 operators are equal if and only if you plug them in here, you always get the same number. Okay, so just do that, and you can prove all these 4 things. It's not so bad. Great. That's for tomorrow. Today, okay. Now we get to some interesting stuff. What we're going to do is fusion. So, bimodules. What's a bimodule now? So, a Hilbert space A with A and B, so these are finite von Neumann algebras, so they're just von Neumann algebras, who cares at this point. This means that I have representations, normal representations, normal star algebra, normal unital star algebra homomorphisms. You have A to B of H and rho going from the opposite algebra of B to B of H such that they commute. Not index, commutator. Okay, so this just says that I have commuting actions on the left by A, on the right by B, and in general we're going to suppress lambda and rho from notation. They're there, but I'm not going to write it because then it's just too many letters. Okay?
So H is at first, it's just a Hilbert space.
H is a Hilbert space.
And then you got to that.
Yeah. B of H. So you're looking at bounded operators on Hilbert space. Yep, that's right, with normal unital star homomorphisms. Right, okay, so I'm not even getting to 2-1 factors today, I'm just doing finite von Neumann algebras. Okay, great. So, skip, great. So, suppose we're going to start with this Y module. We're going to say psi, so this is just my notation that says H is an AB bi module. All right, and again, these are going to be finite von Neumann algebras. They're going to come with their own particular traces. So this one has trace A, this one has trace B, okay? Psi and H is called, so it's going to be left B bounded if the map B omega maps to psi B extends to a bounded operator. And this is going from L to B with respect to the trace to H. Okay, so that's what it means to be a left B bounded vector. Okay, in particular, in what you say, you call this vector LC. Okay, so it's left multiplication by C. That's what it means to be B bounded. You're going to be right A bounded if A omega maps to HC is bounded. And this is going to be right multiplication by C. Okay, so that's what it means to be a left or a right bounded vector in H. Okay, so we're going to denote left B bounded vectors by H naught sub B. Here I'm just forgetting the A thing. We're going to say that right A bounded vectors by A, and then you can put an H naught there, and I'm going to let H naught be the intersection. And in fact, this is dense in H, and a reference is Popper's correspondences. Okay, so you can use some spectral theory to show that H naught, the intersection of those things, is dense in H. All right, and these are called the bi-bounded vectors. Now, there are some easy conditions you can write down on A and B to say when these two sets are actually equal. Exercise, you can think about that. My goal is also to actually take up notes for these lectures. Now I'm saying it, I'm being recorded saying it, so that means that there's some institutional, there's some memory, right? There's some I can be held accountable for such statements. But the idea is I hope to have a lot more details and a lot more things about, for example, some conditions that tells you when these things are equal, and a proof using bounded vectors instead of like the usual proofs that are out. I don't actually know. I know Vaughan has a proof in the 2-1 factor case. We haven't talked about 2-1 factors yet, but and finite index, but we're getting back to that later. Okay, great. So the set of vectors has a right value, a right B valued inner product. Okay, so now here's a quick note about notation. There's a fundamental question is whether or not the inner product is linear on the left or on the right. So the answer is you should have your cake and eat it too, meaning that you have two different notations. One of them is linear on the left and the other one is linear on the right. Use a physics notation for linear on the right, because then you can use the categorical as rank 1 operators, and you use the comma for linear on the left because it's similar to something like a bilinear form, and mathematicians usually have the linearity on the left. Okay, so this is linear here, and here it's antilinear. Okay, so it's actually bilinear. Okay, so what is it going to be if I take, this is defined to be, well, these are bounded vectors, so the only thing that really, the only tool I have is this left multiplication operator. I can take LC and then I can take L eta star. Okay, so this thing actually commutes. This is an operator from L2b to L2b, and it commutes with the right action. And we did all this hard work to show that the commutant of the right B action on L2b is the left B action. So this is an operator of B. Okay, so it actually lives in B. Similarly, this has a left A-valued inner product. Here I put B here. Here I put A here, because it's saying if I take the vector and then I can shove it back into A, here I take this inner product and shove it over into B. So here it's just, anyone want to guess what it is? If you were taking my undergraduate class, you would be like, alarm, he's trying to trick me somehow, right? He wants me to say something with the right operators, but there's actually a trick that happens, okay? So if I just write this formula here, there's a problem because this is linear here. And it's antilinear here. So that formula shouldn't look right. But if you look at this, just like this, this commuted with the right B action, you can check that this commutes with the left A action. Okay? So what I can do is conjugate by J. Okay, since the middle part commutes with the left A action, the conjugation by J commutes with the right A action, and now it's something in A. Okay, so now that's an A. But you really do need those J's. You can't get around it. And there are other ways that you can define these inner products using, for example, the Radon-Nikodym derivative, as in the Evans-Kawagashi book, or in the Bish bimodule paper. They use Radon-Nikodym derivatives, and it's easy to see that this is the same definition. I like this definition because then you get to work with these creation and annihilation type operators, and you can do some fun things. In particular, these are very well suited to doing things like infinite index type things, which I like to do. So, okay, great. So now we can talk about the confusion tensor product. So, confusion, I'm going to write as box times. Okay, so what I do is I take, so I'm going to start with a bimodule, and another bimodule, an AB bimodule, and a BC bimodule, and from this I'm going to get an AC bimodule. Okay, how do I do that? Well, I take first the right B bounded vectors from H, I take the left B bounded vectors from K, I take an ordinary tensor product here. Okay, this is now some vector space. Okay, the A and C actions are going to come along for free at the end, so I want to write some kind of positive semi-definite sesquilinear form on this space. So what is it? Well, I'm just going to say it's the following. I'm going to use my right B valued inner product here. And now this is happening in K. Okay, so by the way, this also, by calling it this, right, b-valued inner product, it also satisfies if I take the star here, it just flips it. Okay, so you can see that from this definition here easily, right? If you take the adjoint of this, it just switches around, right? And it's clearly, the elk C1 plus C2 is clearly linear. I mean, it really is a very easy definition to get all the nice properties about it. Okay, so this gives me some positive, this is actually an exercise to show that this is positive semi-definite, okay? There is a little bit, there's a trick, you gotta do it.
So this is a negative product into the, like, just negative product into the complex numbers?
Yeah, because you've taken this and you've taken the etas and pushed it into B, and now B acts on the left of K, and this is just an inner product in K. So this is actually a number, an actual honest-to-God number. Okay. So now, since you have this positive semi-definite sesquilinear form, it allows me to, I can complete it. To get a Hilbert space, I have to portion out by the length 0 vectors, which is just something you do. In the usual GNS construction, if you don't know your state is faithful, you also have to do that. But we started with the faithful trace, so I kind of, cheated a little bit. This is the completion. Of this modding out by length 0 vectors. All right, so, and this actually comes equipped with a left C and a left A and a right C action. Okay, so here I'm using finite to give this very easy definition of the confusion tensor product of two bimodules. You have to work a bit harder. There actually are some very nice type-independent formulas for fusion that one can do, but we would need to know a little bit more to get off the ground to do that. Any questions so far? Okay.
Something you said a while ago. You said this H circle is dense.
Yeah.
And you said that's by Popper's correspondence. Like how deep is that result?
You can figure it out. You can
You
could just look at it. You can read it, and it's not so bad. You basically
I think if you read it, because I've read it, I think what it says is it's easy to see that. So you won't gain much more from reading it.
So if you parse everything carefully, it kind of
you
follows.
use functional calculus. You take unbounded. You take you take something that's bounded on one side, and then you try to look at it on the other side, but you don't know if it is or not. So the idea is there. It's closable, and then you can do some. You do the usual thing to get. You just cut down by. You use unbounded operator functional calculus to cut it down, and you can. So it's not so bad. I don't think, but yeah, I should check the details. I haven't checked the details in a long time. So maybe we can look at that later if you like. I'm happy to do it. Great. Great, so here's another lemma, which is kind of an exercise, but it's going to help us. So here's, actually, let's do, if B sub H is a dense subspace of H, and B sub K, it's a dense subspace, it's this, I want this to live in H, not B. And I want this to live in K not B, here on the other side, this should be B on the right side, is again a dense subspace of K. These two things together say that if I look at DH tensor over with dk, and I look at the image of this inside.
No, I lied. There's a full proof.
Yeah. Okay. Anyway, the image of this inside here is dense, okay, in this Hilbert space. So I can give you a reference for this. This is done in Michael Byrne's thesis. It's a very nice proof. But also this should appear in the notes. I should, at least give a proper reference to this in the notes when I type it up, okay? But this is going to allow us to do associativity, okay? So that's kind of the point is I could have worked, instead of working with HB0 and KB0, I could have worked with H0 and K0, okay? So that's important. So the next thing is if I have a map, say I'm going from H to L as another bimodule, so this is some bounded operator, which is AB bilinear, okay? And I have another map G going from K, BC to, okay, now I'm going to do something really sacrilegious. I'm going to use M for the Hilbert space, which is just, oh my gosh, why would I ever do that? It's HKLM, that's the next letter. I hate it, but M is traditionally Von Neumann algebra, so Von Neumann is very upset with me right now. So if G is going from K to M, and this is the same as bounded operator AB bilinear, what this allows me to do is I can define an operator F box times G. This is going from the fusion to the other fusion. And again, it's going to be AC bilinear. It's bounded AC bilinear, and it's easy to define. I should just take this box times. This is the image of something in the tensor product. I'll use that notation. Box times is the image inside there. And this just maps to F of eta box times G of C. And this is actually well defined, and it's a bounded operator, and you can do that. Great. So this is bounded. So this is an exercise, let's say. Lots of exercises. Fantastic. Okay, now let's talk about associativity. So, associativity. Of fusion. So what I want to do is, I'm going to use this fact that we have this dense subspace lemma that's going to tell me how to do this. There are also other ways that you can do it, but there exists an associator unitary isomorphism let's do it, I don't know which way, but so here I have K as a BC, L as a CD, H is an AB. This is going to be called alpha HKL. It's going to go to H box times K. So you have to be a little bit careful here, right? Because how did I define this fusion? I defined it by taking all the bounded vectors, right? So if I just look at the definition of this, I have to take all the bounded vectors in this fusion product, and that's mysterious, okay? But I want to define some associative unitary isomorphism here that satisfies some nice coherence properties. Well, I want to use this lemma, okay? So the idea here is I can just say, well, I just take H naught, which is bibounded. This is just this here is dense. This is dense in that. Therefore, this is dense in that. And now I can map this easily over to, in the usual vector space way, right? Here, this is dense, and this is, this is seen to be an isometry with dense range. It's actually an onto. Anyway, it's onto. You're just redoing everything. Okay, so this is just that's what how you define the associator, this alpha HKL. And now it satisfies such that the following is true. So if I take H, I can associate this way, or I can associate another way. I can associate this way, and there is a coherence axiom, right? There are two paths from here to here, and oh, sorry, I need another one. I need a fourth space. This is not good. I've messed it up. Here it's okay. Okay, so now I have four things here, and there are 5 different ways to go. If you know your combinatorics, if you know Catalan numbers tells you there's 5 different parentheses of 4 things. So we can write down what they are. So the first thing, one thing we could do is that's the easy way to go. You just the other way you do it inside. So and then this goes to okay, and this commutes. And the reason it's easily seen to commute is that this, you just look on the dense subspaces, and that commutes. Okay? So it's really easy, and this is MacLean's pentagon axiom. I think, yeah, attributing it to MacLean, I think it's probably a reasonable thing to do. You also have a certain triangle axiom, which is also important. So this is also natural in the sense that if I map from H, say, to H1 to H2 by some AB bimodular map here, then there's each alpha here is more than just an isomorphism. This is it's a natural isomorphism. Okay, so it's natural in each of the H, K, and L coordinates. Okay, so it's natural. So whatever that means. Also, we have there exists natural unitary isomorphisms, and this is going to go here. We've ignored the lambda and rho for the left and right action, so I can use lambda and rho again. I can overload the notation. I can do L2A box times over A with H to H. This is called lambda sub H AB. All right, and you also have box times over B with L2B. This is called rho sub H AB. This goes to H, okay? And these are pretty easy. I'll tell you what one of them is, and you can do the other one. Well, so if I do L2A box times H over A, I can look at A box times C, where this is a bounded vector. It's just going to map to HC, and it's really easy to see that this thing is unitary, okay? Because the A-valued inner product on L2A is just multiplication with an adjoint, right? You take whatever. So that's easy to see, so this gives you some unitary isomorphism here. And moreover, it satisfies the following triangle axiom. Coherence. as follows. So if I do H box times L2B box times K, I can associate this differently. This way, one thing I can do here, I can go downward and I can, here I can do, this is what? Row box times the identity, right? So I know I can do this box times of bilinear maps. So here, this is a box times of bilinear maps. This goes to, and over here, I'm doing the identity of H box times lambda, okay? And this commutes. And it's really not so bad. It's because the point is that if I take, this is just basically saying that eta b box times c is equal to eta box times bc. Okay, it really just comes down to this, and this is the image of eta tensor c in the fusion, right? You take the ordinary tensor, this is just saying that eta b tensor c minus eta tensor bc is in this kernel. It actually has zero length. Okay, and that just comes from the fact that this left b valued inner product is bilinear. Okay, it comes from the bilinearity. It's really not so bad to see this. Okay, so this actually tells you that you have this triangle coherence axiom. Okay, so what have we really done just now? We've done so far in these 53 minutes. What we just did is the following theorem. There is a 2 category. So 2 category, some people call this a bicategory because it's I mean this in the weakest sense, but so maybe you should look up, if you care about the axioms, you might want to look up bicategory, but I say 2 category. There's a 2 category whose objects are finite von Neumann algebras. One morphisms are bimodules, and 2 morphisms are intertwiners. Okay, and this does the whole business. It actually we've constructed the 2 category.
You define intertwining?
Sorry? The intertwiners are these AB bilinear maps between. So let me write it down more explicitly.
So there's a difference between bicategory and 2 category, whether the composition of one morphism is strictly associative or not.
Yeah, it's this coherence business, right? The fact that I have these, associators which are satisfy this pentagon coherence and the triangle coherence, and this is this weak version of 2 category, which is called bicategory, but I think it should be called 2 category, personally. So, since I've got the chalk, great. So yeah, here you can say, so objects are here. One morphisms from A to B, so it's just these H A to B, right? These bimodules, and then the 2 morphisms are these F going from H A B to K A B, which are bounded in bilinear. Okay, so this is the and these are the axioms you need to prove essentially. Okay, so there's more structure for this 2 category. Okay, this 2 category is the thing we're talking about, and I'm avoiding category language, but I also don't want to avoid it too much because the connection between category theory and subfactor theory is very tight, and so we shouldn't, we should accept the category theory. We should open it into our arms and to see how useful it can be, and also it will give us interesting things to do later if we open our eyes to that. So this 2 category has a dagger structure which is W star. Okay, so what does this mean? So
So you're trying to
What's another example of a two category that I might, you know, that I might.
Category of all algebras, bimodules, and intertwiners. Not binomial algebras, just algebras,
This is
bimodules,
basically
and
what I
intertwiners.
actually think it's just one of structure for that sort of mathematical object.
Yeah, and the point is you can look at, subcategories of this algebras, bimodules, and intertwiners. This is a subcategory of that, right? You're looking at particular algebras with, equivalent traces, particular bimodules, particular intertwiners. Right? This is the other thing I said is just completely algebraic, but this is what you would call people would call a 2-vec or something. This algebras, bimodules, and intertwiners. This is like this is kind of like this is like if you're looking at some kind of topological field theory, this is what you would take values in or something. And this is maybe not motivation for you, but
No, I'm just trying to get for you. I mean, so
Yeah.
when people say this is a category, I know what one of those is, but when people say this is a two category, I want to get a feel for what the other sort of things
so it's like it's
So
a
this
tensor
box,
type, like,
this box times thing is part of the two category structure.
yeah, this is the composition of one morphisms. So so the point here is just the one morphisms are composed by doing box times. Okay, two morphisms here, you can do two different compositions. You can do the box times ones, or you can just compose, right? If I have h to k to l and they're all AB, I can just compose linear operators. And it turns out that they satisfy the exchange relation, which I didn't write down, but that's a good thing to point out, that if I did F1 box times G1 and F2 box times G2 and I compose that, that's the same thing as composing, and then box time. Okay, so this is not hard to see. You just check it on elementary tensors and everything works just spectacularly. So the two category has a dagger structure. What does this mean? It says for every H, AB, and KAB, there exists a map star from Hom H to K to Hom K to H. This is the two morphisms, okay? So it's F maps to F star, okay? And now it's such that, one, it's involutive. What this means is that if I do lambda F star, I get lambda bar F, right? I can these Hom spaces are linear spaces, right? These are linear maps between Hilbert spaces. So I have this. That means it's anti-linear. I have, if I take F star star, I get F. And finally, if I have composable F and G, and I take their adjoint, then I get the adjoints composed in the reverse order. Okay, so great. Moreover, two, if I take this box times and I take its adjoint, it's the same thing as the adjoint, the box times of the adjoints. G. Okay, so that's another thing it satisfies. Three, the maps alpha, lambda, and rho, these are the coherence maps. Here, this is the associator and the uniters. These are unitary. Okay, I mean, that's a unitary, this is a unitary. And then four, so this all tells me it's a dagger structure. And now I'm saying it's W star. Four, since we can take direct sums of bimodules, and this is a cheat, because I can take direct sums, the fact that it's W star boils down to the fact that for every H AB, the endomorphisms, the AB endomorphisms of H is a W star algebra. It's a Neumann algebra. W star algebra is just another name for the Neumann algebra, and here in general you don't call them the Neumann categories, you call them W star categories. Okay, so that's why I'm saying W star, but if endomorphisms of every bimodule is a W star algebra, why is that the case? Well, this is just, I take B of H, I have this action of A, so I take A prime, and I also take B opt prime. These are all the Neumann algebras, their intersection is a Neumann algebra. Okay, so this is a Neumann algebra, therefore this is the W star property. Okay, so this tells me I have this unitary two, this is sometimes called a unitary two category, or a W star two category might be the best thing. I think I'm probably at time, a W star two category. Okay, so I'll stop there, and next time we will talk about the other involution. This is one involution, there's another involution that is also very important to the story. Okay, and we'll go on from there.
Okay, so thank you very much.
Thanks.
Are there any more questions?
In 4, so if A and B are both finite, is this endomorphism thing also a finite non-endomorphism?
No, right? So I think the answer should be no. And the easy way to see that is if I take A and B are both the complex numbers, and they're the same algebra, then it's B of H.
Yes, imagine you have an application.
Is there an infinite Neumann algebra that admits a faithful trace which is not normal?
A faithful trace, which is not normal.
Because the definition of a finite Neumann algebra always says that there exists a faithful normal trace. If you have a faithful trace. I know there are singular traces.
If it's not, if it's a factor, no. Because there's no. I think the answer should be no if it's
Does it dictate what?
a factor. What?
Yes.
If it's a factor, you've only got the one trace.
So, well, I mean, yeah. So if it's infinite and a factor,
And if it's not a factor.
there's no trace. If it's not a factor and a faithful trace which is not normal.
Well, I'm wondering whether, the question is whether you need the word normal in the definition of finite Neumann algebra. When you say it has a faithful trace, whether you need the word normal is necessary.
If you have a faithful trace, doesn't that show that you've got projection sub-equivalent to itself? Then the difference must be, yeah.
So you're saying it's completely additive because if I take.
No, I mean, I just want to go.
If you have a faithful trace, then you can show it's finite in the other definition of finite. Right?
In the original definition of finite, i.e., there is no the unit is not sub-equivalent, doesn't have a projection sub-equivalent to itself.
Saying the word normal is not necessary.
So you can say that means it's a finite Neumann algebra.
Yeah, in the
But the question is whether or not the trace is. So are you saying whether the trace is automatically normal, or are you saying whether or not the?
no, what I'm claiming is
Yeah, that I believe. Yeah.
if there is a faithful trace, then there is a faithful normal trace.
Okay.
I'm not claiming the same
Well,
trace is faithful.
Okay, okay, that answers that.
With suitable like separability conditions, right?
I would hope without, to be honest.
Because I think if you have, you can do big things, right? I think in Takasaki they require.
Yeah, but you're insisting that there is a faithful trace in the first place. which
Yes.
is very
Okay.
strong.
If I assume there's a bit, yeah.
So
then
the
that's-
claim I think I'm making is that if there's a faithful trace, then there's a faithful normal trace. But I would want to I wouldn't want to
You'd
actually.
want to check if there's a
Yeah.
faithful trace that you get the right separability or something.
Yeah, I don't really. Yeah, I mean, we need to be checked, but it sounds very. I mean, certainly you should get finiteness.
You certainly get
in the old-
finiteness from a
in the
faithful
old
trace,
definition. Then you need to. Of course, once you have finiteness, you have a separating family of faithful normal traces.
And
So
then
the
you
only-
want to take like one
want to
over
argue
one
that
over
there is
2 to the
one
end.
of
Some,
them, it may be a bit strong, but
so
it's
there's some
certainly.
separability. I thought. But, anyway. Well, I guess yeah, but you don't need separate anyway.
Any more comments?
Yeah, maybe it's more standard to call those tracial Van Neumann algebras than finite Van Neumann algebras, which I can do tomorrow. Maybe I'll say tracial tomorrow rather than finite. Certainly they are finite, and maybe not all finite Van Neumann algebras have this thing. Ones that act on separable Hilbert spaces.
Any more questions? No, thanks again. So we have a break for tea and then start back at variable.
Well, they need not be.
That's essentially the end of stuff.
That would be called
Yeah, so my nodal category is two categories with one object.
Classical definite is.
I'm getting to that. I'm gonna do a graphical coding thing tomorrow. Yeah, it's exactly the,
First of all,
if you, a
if
nodal category